So let's repeat what we did in single dimension with many dimensions. We have an objective function where we feed it a multidimensional vector, get out one scalar value. We could say let's approximate that using a second order Taylor polynomial. So go ahead and write out the Taylor polynomial at kind of vector x0. Best to use linear algebra notation if you can. So I'll pause the video while you do that. Okay, welcome back from pausing. It's my current function value plus the gradient times the difference between my current value and whatever new x value I'm considering, plus 1/2, which is like 1 over 2 factorial, right, from the ordinary Taylor series, times basically something transpose matrix times that something, and h here is the Hessian. And then what is the minimum of that? We would need kind of the vertex formula, but in multiple dimensions, which we derived up here. So the minimum would be basically the same thing we did before, where we call this C, we call this B, and we call H the A value, or Q, except we're combining the 1/2 here. And so filling stuff in this kind of vertex formula, we end up with a 1/2 inside of an inverse, which becomes a 2 and cancels the 1/2 here. So we get negative Hessian inverse times the b vector, and the b vector is the gradient. And remember that's the difference between kind of our current position and where the new minimum is, at least of this second order approximation. So my new position should be my current position plus negative Hessian inverse times the gradient. So that's Newton's method in multiple dimensions, except it has a basic problem that we need to think about. So that's one of my questions here. First, what will happen if the original objective function is exactly quadratic? And can we improve on what I'm saying here, because f might not be exactly quadratic? So pause that and think about it. All right. So just like before, if f is exactly quadratic, then its Taylor approximation in second order is exact, and this will jump exactly to the minimum in one step, which is a pretty good idea. But since f is not usually exactly quadratic, we wouldn't want to jump directly here maybe, but just take that as a direction to look in and do a line search, rather than using the exact length of that vector. So that brings us to another follow-up question or two. Try rewriting this with a line search kind of flavor to it, like have an alpha somewhere, and alpha is a thing you can adjust to do your line search. And then think about what's a natural first value to try for alpha and why. Okay, pause the video while you think about that. Remember, you're trying to turn this into something with the flexibility to do a line search. All right, so because we're saying here's where I am now and this is the direction I'm going, we would just say let's put a scalar multiple on that to say how far in that direction I'm going. So I just put the alpha there. And then because there wasn't an alpha there here, that's like saying alpha equals 1, and then we don't have to write it. So that's saying alpha equals 1 will jump you exactly to the new minimum if the original objective function is quadratic. So alpha equals 1 is a natural first guess, and I mentioned that before, but finally we're seeing why. And we should also mention that we're talking about line search inside multidimensional Newton's method. And you don't have to do single dimensional Newton's method for line search inside multidimensional. You can kind of mix and match. You could do multidimensional Newton's method with golden section search as the line search. You could even do steepest descent as the multidimensional version and Newton's method inside that as the line search, one-dimensional Newton's method. Usually, if you're doing multidimensional Newton's method, that means you have the gradient and the Hessian easily available, and so maybe then you want to use them in doing the one-dimensional line search to make things more efficient. But there's not a hard and fast rule that you have to do it. If you do have those available, it's a bit of Calc 3 and linear algebra fun to say, how do I take my multiple dimension derivative information and use it to get derivative information along this particular search direction. So you can go look that up if you want to, or send me questions.